video. In this video, we will be looking about PIC12F675 8-bit microcontroller. Whenever you use a new device, you know the datasheet is the best friend of yours. So we will be directly jumping on to PIC12F675 datasheet, which says it is an 8-pin flash-based 8-bit CMOS microcontroller. So let's go down below. Here you can see on the general overview, it has only 35 instructions to learn. It has DC to 20 MHz oscillator or clock input, and also it has interrupt. Also in the peripherals you can have 6 IO pins with individual direction control, high current sink, current source for direct LED drive, one analog comparator module, programmable on-chip comparator voltage reference module, and also you can have the ADC 10-bit ADC programmable 4-channel input. It has 4 channels, and it has a timer of 8-bit timer, and also an enhanced timer 1, which is a 16-bit timer. Also you can have the ICSP headers, and also you can have the general features. You can read them below. Now the main thing comes here. I am using the PIC12F675, so it has only 1 kilobyte of flash. For program memory, it has only 1 kilobyte of flash. On the SRAM it has only 64 bytes, and in the EEPROM it has only 128 bytes. It has 6 IOs and 10-bit AD channels, 1 comparator, and 1 8-bit timer and 1 16-bit timer. So the pin out here, you can see VDD plus 5 volt, BSS, ground, and these are the GPIOs you can see here. And here we can see the OSC1 and the OSC2. You can use a crystal oscillator here of 20 MHz for maximum speed, but I'll be not using an external crystal, since you will be then wasting this 2 GPIOs. So I will use the internal 4 MHz oscillator. If you see here, it has a precision internal 4 MHz oscillator, factory calibrated to ±1%. I will use this 4 MHz oscillator, internal oscillator, so that I can use all of these 6 GPIOs. So that's why I have not used any oscillator here, any crystal oscillator here externally. I have used the internal 4 MHz clock. Well, in a previous video, you may have saw using the 80x13. It is also an 8-pin DIP, and our present microcontroller is also an 8-pin DIP. And observing the datasheet here, the 80x13 too has a 1 kilobyte of flash, 64 bytes of EEPROM, 64 bytes of internal SRAM, and our present microcontroller is also have 1 kilobyte of flash, 64 bytes of SRAM, and 128 bytes of EEPROM. So you may say that this one can be a competitor of this one. They both can perform similar tasks. You may look at the datasheet for both for getting further details of which one is more powerful or not. So that's for another discussion. So let's now focus on to this microcontroller now. So let's move on. Now we can have the general contents from here. Right now we will be seeing the GPIO port, since we will be using this to do an LED blink pattern. So we will be looking directly into the GPIO port. Here you have the trace IO registers. Here you have only one trace IO register and a GPIO register. Firstly, the GPIO register, here you can see the register here. It has only 6 GPIOs, so only 6. Rest are unimplemented, read as 0. And these are general purpose IO pin, GPIO register. These are identical to if you use PIC12F675, then this can be identical to like RA1 or RA2 like. And now we have the trace IO, the tri-state register, similar to the PIC12F675 where you have the trace A, trace B like that. Here you have only one port, so that's why you have only trace IO register, a general name trace IO. So trace IO 5 to 0 for the 6 bits, recipe or unimplemented, wait as 0. As usual, if 1 then it is an input, then GPIO is configured as an input, and if 0 then it is used as an output. Unlike KVR microcontrollers where you have 1 for output and 0 for input, there you have the DDR register here in place of the Tris IO. So anyway, remember these facts here. Here you have also many others register here. We may look at them in a further video. So right now we will be using just only this GPIO register and this Tris IO register. This Tris IO register to set the pin as an input or output, and the GPIO register to read or write value. Now I have made this board. You can see the PIC12F675, and these pins are for the PIC3, for the PIC3 connection, ICSP connection. And here is a switch so that you can switch on to program mode or run mode. Whenever you use the PIC to program, you need to switch it to program mode, and when you are trying to run the sketch, then you toggle the switch to run, and you can run the code present inside the microcontroller flash. And here you have the LED connected to GPIO 0. So you can have the circuit diagram in my description given below. You can find the link given there for the circuit diagram. So now we can use the MPLAB IDE for writing a simple Blink sketch. Now in a Blink sketch we will use a certain a pattern, like to vary the rate of blinking from high to low and then again low to high. We will be seeing in the code right now. So firstly you can have in the void main Tris IO 0 equal to 0, since we will be using the Tris IO 0 pin as the output. So 0 means output. Now while 1, so here you can have an integer variable I running from 0 to 500, and I plus equal to 100 means I equal to I plus 100, and blink I, meaning that the blink rate will change as I will go from 0 to 500 with increment steps of 100, and then again from 500 to 0 with decrement steps of minus 100, and then again there is the blink I. Now in the blink I we will just toggle the LED, blink the LED 1, GPIO 0 equal to 1 output. You saw the GPIO register in the datasheet, the GPIO register here, GPIO 0. We can directly access the bit. XC compiler actually allows to do that. So directly by bit accessing you can write 1 or 0. So GPIO 0 equal to 1, then a small delay, and then again GPIO 0 equal to 0, then a small millisecond. And inside this void delay you can have this function for generating the delay. Now you will be thinking that why I am writing this separate function for delay when I can directly write this delay here. See what will happen if I do this. Actually underscore delay underscore ms is the actual function, and this one is the custom delay function where I am using this same here, this underscore delay underscore ms, which is the library function. So what if I directly use this library function here in this code? So what will happen if I compile this code here? So I'm building this code. You will see it will actually generate an error. So let us see what the error comes. So here you can see the error. So here it says inline delay argument must be constant. So this actually means we cannot use a running variable like I here. We have to use a constant 1000 like value in here. As you can see here, we cannot use a running variable like I. So the solution actually I have found from the a forum here. Someone asked how to use the variable in delay underscore ms. So here one has suggested to use a custom delay underscore ms, but we are using the same underscore delay underscore ms library function with a parameter of 1. So this will generate 1 millisecond delay, and here you have the parameter milliseconds. So suppose if we generate 100 milliseconds, so this loop will run on 100 times, in each iteration it will generate 100 millisecond delay using the same library function __ delay _ms. So in overall this will again generate the same 100 millisecond delay. So in simple words, this function is actually using the same library function __ delay _ms, but we are just bypassing the problem here which the compiler generates. We are just using this clever tricky method so that we can bypass the problem which our compiler generates. So we have implemented that thing here. So I am again reverting back to the actual code. So that's why I have used this void delay _ms, the custom function, and inside this custom function we have the same library function __ delay _ms. So the number of milliseconds we will write, it will loop for that particular number we will mention here, and at the each cycle it will generate this the 1 millisecond delay using the same library function. So this is nothing, just a simple problem for the compiler, and it can be easily bypassed here. So now again we can compile, and it is just a small warning for me to understand it, not a big deal. So our program is successful. So you can see the program memory is only 1 kilobyte, and it has almost consumed up to 95 bytes of memory, or almost 9%, and data memory up to 17%. Don't forget to write this defined external frequency of 4 MHz. We have said that we will use the internal clock of 4 MHz here. The internal clock can be set in the pragma configuration bits, and also the MCLR enable is on, and the external frequency is thus set to 4 MHz. So we will be uploading this code using the MPLAB IPE, and we will be seeing the code in action. Let's see. So our small microcontroller board is connected to PIC3 here. So after uploading the code, I have set it to run mode, and now see the flashing. The delay time will vary. It will slowly decrease and then again increase. You have saw the 2 for loops there. It will do this work. You can have the circuit diagram of this small board in the description link given there. You can see the circuit diagram. It is extremely simple. So our code is working just fine. As expected. And now you can find this code in my GitHub account, link given below, so that you can tweak various values and you can generate more pattern of your own. And in our further videos, we will be using this microcontroller to use more peripherals like the ADC. Also, you can use the EEPROM and interrupts. We will be seeing them in a future video. And in the meantime, don't forget to read the datasheet. So thank you for watching this video. So please like, share and subscribe, and for any confusion you can comment down in the comment section below. I will definitely try to solve those problems. Thank you for watching this video.